morning, everybody. It's a pleasure to be here. My name's David Hodgetts. I run a company called VRGS Science Limited, and I specialize in the development of software for digital outcrop modeling. A bit about my background. I'm an ex-academic. I spent about 20 years at the University of Manchester as a lecturer in geology and teaching digital outcrop modeling and digital data collection techniques and subsurface modeling. What I'm going to do in this first part is give you a little bit of an overview of VRGS and what it can do, but talk about why we do digital outcrop modeling, the sorts of results that we can get from it, and along the way we can think about how that can be applied to planetary mapping. All right, so let's go. I'm gonna these are the things that we're going to talk about along the way. So I'll look at different ways we can collect data and how we can go about analyzing it. We'll talk structural and sedimentology. Really, when you're dealing with this kind of outcrop modeling, everything is together. So you have to sort of work with an integrated approach, thinking about structure and sedimentology together. And I'll also go through a little bit at the end on what can be done with machine learning and AI on this kind of data as well. Why do we do this though? What are the point? Why should we collect data digitally, and why should we work digitally on these kinds of data sets? An ex-PhD student of mine has put together a paper which covers why you should work with digital outcrop data. And what it allows us to do, so if we think about on Earth, we can go out and collect data in the field quite easily. It makes that data a lot more accessible. Now, accessible means that you can run lots of the outcrop that you can't normally get to. And that's exactly the problem that we have with planetary mapping. We can't get to these outcrops. So if we can have some kind of way of collecting them digitally, like we've got now, it makes them a lot more accessible. It makes it that more people can study that data and work on it. That allows us also to be a lot more quantitative. We can make direct measurements from our outcrops. We improve our statistics, and we improve the quality of the science. Same on planetary mapping, same on the Earth. That also leads to reproducibility. Now, on field geology, when we think about what we do back on the Earth here, reproducibility has always been a problem with field geoscience, because it's quite often the case that people can't get out into the field to look at the work that you've done. So having things digitally allows you to be reproducible. So all these shape models that we have for the comets and the planets, they're available to the wide scientific community. So any work that's done on them can be reproduced. And then we have a lot of things about preserving the data sets for the future and geoheritage and all these sort of different things, and building virtual field trips. And there are companies which specialize in developing virtual planetary field trips as well. Well, the kinds of approaches that we deal with at the moment for digital outcrop modeling is we have LiDAR mapping and we have photogrammetry. So LiDAR is a system. It is quite expensive to do. It requires you to carry stuff around in the field, and you can collect these really high resolution three-dimensional models. The great thing about LiDAR is that you know what the accuracy is. So, you know, your LiDAR system has a specification and you know exactly what the accuracy of your data is. The downside is that it's quite expensive. On the other hand, here we have photogrammetry, and Both these systems are used on planetary mapping as well. So, you know, we've seen from the Mars rover quite a lot of photogrammetric models being produced. And on small bodies, people are using photogrammetry as a way of reconstructing the shape of these small bodies from image data that's been collected by various missions. The outcrop model that you see here, I collected that just with a digital camera and a handheld GPS. And that's, you know, all the field equipment that I needed to do it. You take it back, you can process it and generate a nice 3D model. So it's really cheap to do. It's very easy to do, but the downside of working with digital outcrop data with photogrammetric data like this is that you don't always know the accuracy of the resulting model. Right, a little bit about VRGS. I started developing VRGS back in 2003. I was working on collecting digital outcrop data sets from a variety of different locations and different sources, and I wasn't able to do what I needed to do with the data. So there were bits of software out there that could visualize it, and I could do some interpretation, but that interpretation wasn't really done in a geological way. It was more done in a civil engineering sort of way. And I started work on VRGS. So that was back in 2003. And the first publication was around 2007. And then in 2020, I decided time to do something different with my career. And I basically spun out VRGS from the university as a company and formed VRGS Science. So that's what I've been doing since then. I'm a big advocate of geoscientists learning how to program and being competent with software and being able to actually take data and process it. And if you do have some programming background and with a little bit of effort, you can come up with a commercial software application like VRGS and go on and do something with it. So I encourage you all to actually go out and learn some programming if you don't already have some as part of your current courses. What we see in the 3D data sets on the outcrop is only part of the story. We've got these nice photogrammetric models, which are photorealistic, but there's a lot more information in there. And that's the same with these shape models that we get from planetary bodies, that we can see the geometries of them, but there is more information held within that mesh that we can get to. And we do this through a process, it's attribute analysis, as I call it in VRGS. And what we do there is we go through each vertex in the mesh. So your mesh is made up of vertices linked together into triangles. You can see on the image here. And those triangles then have in outcrop modeling, have a texture map attached to them. And that's what makes it look like rock. So for each one of these vertices, we look at all of the vertices that lie within a certain radius and then do an analysis on them. So we could do a best fit plan and work out the orientation and look at curvature and look at how linear those points are. And there's currently, I think, about 20 or 30 different attributes that you can generate based on a small area like this. And each will tell you a little bit different about the data set. And then we can apply that at a whole range of different scales. Here's a desert rose. So scale bar there is only 5 centimeters, but the same process that we can apply on outcrop models and on a planetary scale, we apply here. So we're looking at the orientations of the different petals within the desert rose, and we can plot those on a stereo net to understand the distributions. Now, thinking a little bit ahead to what we're going to do when we look at 67p, these sorts of techniques work very well with mapping fractures and bedding planes and like terraces that Matteo just mentioned on 67p. we're able to use a whole variety of different attributes to help us find features and map features that aren't always clear in the photorealistic model. And here's a data set. This is actually from the Jurassic near Whitby in the UK. And I've interpreted a lot of fracture planes, and you might want to know about fracture distributions back on Earth for things like carbon capture and storage, geothermal, and of course traditional oil and gas production relies on knowing things about fracture distributions. But the attributes allow us to pull out a lot more information. So on the top one here, we've got orientation. And on the lower section, on the right-hand side, we have, this is coplanarity, so how flat the surface is. So those are the sort of information you can pull out from outcrop data. If you are looking at other kinds of distributions, so we might want to look at bodies in outcrop modeling terms that I use, we call these geobodies. In this example, this is from down in Spain, in the Huesca fluvial fan. We want to understand the shape of these bodies that we can see on the outcrop. They're too big for us to go and measure in the field. You know, you can't have a tape measure that's, you see 300, 400, up to 600 meters wide. And a lot of these you can't get to. So you're doing all of this work remotely. We want to be able to understand the shape of them. The shape that you see on the outcrop, or the width, is an apparent width. To know what the true width is, you'd need to know the orientation of the body. So we use paleocurrents to work out what the orientation is. And then we can, from that, we don't just do it from one paleocurrent, we do it from lots of paleocurrents. And then that gives us a range of possible sizes for each one of these bodies. And all of that information can be taken in and used to build a 3D model. So these are geocellular models built to show what these features would look like in 3D if we were able to slice through the outcrop and slice through the ground. We have a lot of uncertainty when we deal with outcrop models. And when you're working with planetary data as well, you also have a lot of uncertainty. And it is really important that when you're dealing with these kind of data sets, that you understand the uncertainties that you're dealing with. And particularly when you go on to do research with these kinds of data and start to publish, is that understanding of where the uncertainties are will really help improve the work that you do and allow people to know where to improve the work that's gone before. So understanding uncertainty is important. Other kinds of measurements that you can make, here we've got sedimentary logs or measured sections, so measuring different stratal thicknesses and working out information about those strata. Typically, if you were a field geologist, you would be doing this with a tape measure and you'd be adding in grain size measurements. We can't get grain size here, but we can get a lot of other information. So as you go up through the outcrop, you can click points on your bedding planes and main surfaces. And then what happens in VRGS, that as you click one point to the next, it tracks its way through the mesh and extracts all of the different attributes that have been generated. So the attributes that we just talked about, like the dip direction, coplanarity, and then it plots it like a sedimentary log or like a geophysical log. And here we've got surface orientation. This is the color that's been extracted from the texture. Then we have all the different attributes, or some of the different attributes here. And then this other second color track is actually an average of the colors in an area around the points. And this enables us to start to bring out the physical measurements that are also linked into our data sets. And of course, we would go in and on, when we were back on Field Geologists on Earth, we would be able to add in grain size information. We could take these back out into the field with us as templates and then go to these localities and actually fill in what the grain sizes are, and then we know everything is accurately georeferenced. Another important thing to realize when you're working with any kind of data, whether it's like on Earth or planetary, is that georeferencing your data is of great importance. Being able to know exactly where any piece of data has come from makes your work reproducible. So make sure everything is georeferenced when you collect data. There's other things that we can do with the measured sections here. This is an example from an outcrop study from quite a few years ago, back in 2014. And we generated a section that ran along an outcrop. And this approach is creating what's called an orthographic projection, or back in these days, I called it a projection plane. But an orthographic projection removes the effect of perspective from the data, and it allows you to make accurate measurements off a 2D panel. We can tie in measured sections and then be able to do deterministic correlations between those measured sections. Another thing that you can do with this kind of orthographic projection is you can flatten it. So this top section has the orthographic projection behind the correlation panel. We can flatten it, and then we can look at thickness variations as well. Or you can do vertical exaggeration to highlight subtle features. And again, these sorts of techniques are applicable on any kind of data that you're working on. Something that'd be really interesting to do with small bodies, listening to Matteo's talk and thinking about sublimation and the lifespan of these bodies is, you know, if you could get time lapse, so the next time that the body comes into the solar system, being able to make another model to see exactly how they change and where the changes are. We do this kind of thing on Earth. So here's an example from back in first data set collected in 2017. This is on the Yorkshire coast in Whitby, and one in 2022. And by comparing the two models, you're able to show exactly where on the outcrop you've had erosion. This one is showing that in this area, we're probably looking at erosion by sort of low frequency, high magnitude events. So these are rock falls that are happening once every so often. But you're able to do monitoring. Now, what I thought was, you know, really nice about this study is when I collected this data set in 2022, I didn't do it with any intention of looking at time lapse. I just wanted to compare the performance of the two drones. So these were two different drones, a Phantom 4 and a DJI 4 Mini, sorry, a DJI Mini Pro 3. And I just wanted to compare the difference between the behavior and the image quality. But once I'd done it and done the comparison, you know, these variations just sort of fell out of it. But that's maybe something to think about for the future work, is time-lapse comparisons of bodies over time. Well, this problem is equally applicable to planetary mapping and to what we have on Earth. We have a whole range of different data types that we have to deal with and integrate all of these into different bits of software and try to bring them all into, much so with VRGS, the aim is to try and bring of all these different kinds of data sets into a single integrated environment where everything is properly georeferenced and related to one another so you can do your analysis. So we have logs, structure from motion, photographs, elevation data, thin sections, and a whole range of different data types. And that leads to a problem that we have with standardization of data. There are so many different data formats out there. Big problem in digital outcrop modeling. I don't know so much about in the sort of planetary mapping world, it might be a little bit better. These are all outcrop model formats, as is SLPK, as is GLB. So they're sort of 3D model formats. Image formats, LiDAR formats. That's a LiDAR format. LAS there. We also have LAS, which is a geophysical log format, just to be very confusing with the LiDAR-based LAS. But the data type things we're looking at for the future, really, ones I think you to look out for outcrop models, OBJs and SLPKs. That's where we're going. So most of the shape models that I found are available in OBJ format. That's a good format to people to use. SLPK is very good if you're dealing with very large models and you want a tiled model system. It's called a scene layer package. The other one that's very common and very useful for us all is GeoJSON. So I know you've been looking at using GIS systems like QGIS. GeoJSON is everywhere at the moment for spatial mapping, and it's a really good, straightforward, simple format. You can get very complicated data sets, and even if you've got very basic programming expertise, I mean, really basic programming expertise, you can get a GeoJSON file and understand what it's telling you. And then we have this one down there, is the universal scene description, which is becoming more popular. And USD is the format that is driving the metaverse, and it means universal scene description. It's actually been developed by Pixar, but that is gaining real popularity as and it's often called the JPEG of 3D. Can we use machine learning and artificial intelligence with all of this kind of data? Well, yes, we can. We've got these digital data sets that lend themselves to it. The problem that we have in outcrop modeling, and I'm sure you actually have in planetary spheres as well, is that at the moment we don't have enough training data to really make things like machine learning and deep learning work for us. And by training data, I mean actually good quality, accurately labeled data, which is what you need for machine learning. But within VRGS now, you can have an integrated Python editor. So all of your machine learning libraries can be used against your digital data sets. Here's an example. This is using scikit-learn, but you can use TensorFlow or develop your own approaches as well. Anyway, that's my introduction to VRGS, and I think that's brought us to 1:15. So I'll leave it there. We're going to, after, so if there's some questions, I'm happy to answer those, and I will go on to looking at actual data after the break.